Oh, I think we're on. Just verified. Got some internet stuff going on here, I guess. But in any case, let's go ahead. Hi, I'm Howard. We're back again. And this is going to be a complete start to finish of the EMPATH based on a lot of requests. So we're going to go through everything from setup and you name it. First, I'm going to show you the system that we'll be simulating because I don't have a 600 horsepower pump with a VFD present here, but I do have the data. So we're going to simulate it with a simulation motor so I can demonstrate the data collection part, and then we're going to go into the real data to analyze. So in any case, here is the system setup that we're going to be analyzing. This is the VFD on the output. One thing I want you to notice is I put a current clamp around 1 of 3 on each one. Okay, so that'll be important when we set up our CT ratio. Okay, now yes, I could have probably gotten around 2, but really that makes it really strange when setting up that ratio. So just around 1, still get good results. And then here on the right, that's where we set the system down. On occasion, depending on the rules and depending on what's here, I will put this inside the cabinet and shut the door and usually find a vent to run my cable out to the laptop. And in worst case scenarios, I have put everything inside and run it as a data, for something I'll show you in a little bit. On the motor in question, here's the nameplate. I'm going to show you how to deal with the bearings here in a minute. But let's go up here and we have 600 horsepower, 1789 RPM machine at 632 amps, 460 volts. I've written it down for the data entry portion. 60 hertz, and this is the 10%. Because this machine's allowed to go down to 10% of 60 hertz. And in a variable torque environment, that's why it shows 0.6 horsepower at 6 hertz. Okay, 1.0 service factor, insulation class F. Most inverters, inverter applications, this is specifically an inverter duty motor, but if you apply a motor on an inverter and it has a 1.15 service factor based upon design rules, both IEC and NEMA, that becomes 1.0. Okay, and a 1.0 you have to derate as well. All has to do with temperature. Okay, so 5012Z or 5012Z frame. It's a good size machine. It's got some issues. I know that already. So down here's the part. So this is a 110 BC 02. Okay, so I'm concerned about this BC, I'm concerned about this 02 and this 110. Everything else are other features of the bearing. And what you do is this. Not look at a blank screen, but this. So I happen to select this one. Most of the manufacturers have them. And it will help us analyze the bearing. I used a couple of different ones, including the manufacturers sometimes have them as well. In the meantime, as we go through, if you have questions, go ahead and put them down. I'll be watching questions and I'll get to them as I can. So in this case, I'm going to skip to the back because I know where the stuff is because I use this more often than I care to say. So 110, that's 1. That is going to be the inner race dimension. Okay, and 2 is going to be, here we go, bore diameter. 2 is going to be the type. So this is a BC. So this would be a 6000 series bearing. And then the 02 means it's a 200. So it's a 6200 bearing in this case, because it's a 110 BC02. So the 110 now we want to go back to the 200 series, 6200 series bearings and look for the bores. Let's go back. Okay, so I think, is this it? No, that's loading. Okay, dimensions, here we go. So I'm going to look for the bore, which was 110. So it's a 6222, which I had written down incorrectly last night because it was late. So it's a 6222 bearing. I'll note that on both of them. I'm going to randomly say the pump bearing sizes because I didn't write them down. So it's a 6222 bearing. Okay. Come down here, 110, 6222. That takes care of our data. Bear with me just a sec. I got to switch. Where are you? Switch locations here. There we go. And let's go to this monitor here. So you should be seeing all kinds of stuff on the screen. Let's move this. And I don't need to be staring at myself. Okay, so let's go ahead and we're going to close this out and we're going to take a look at here. So I have a demo motor set up over here to the side on a VFD. It's going to run up to about 30 hertz. You may hear it. It's hooked up right now via, here, let's see if we can see it here. There we go. Whoop, right there. So motor drive, power supply, and there's the EMPATH here. Okay, so I am using this with the, there we go, with the other stuff. So back to what we're looking at on the screen. Let's make sure we are, and here we go. Okay, so we've got, we open up the software, we get this. First thing I want to do is make sure my settings are correct. So we'll go to Setup Options. This, by the way, is 7.1D. The released version is 7.1C. There's no difference. So coming on here, this is the serial number, first one of this design. And then I want to make sure that these are here. I can select Display Hints. You can see that as I'm moving around, it's telling me things. In this case, we're just going to leave it at default layout. For certain types of things I do, including wind turbines and things like that, I will set up the screen specific ways. So you have the option of going in, setting up your screens the way you want, and then you hit save, you click user and save, and every time you open it up, it'll show you exactly like that. Fantastic if you're doing a lot of equipment. Acquisition, I'm going to leave the error thing out, start with numeric display. Most of these are default. I turn off the calibration warning. You can leave it there, just tell you after it was calibrated 365 days ago that you need to be calibrated. I can take a block size. Most machines right now, most electrical signature analyzers are down in this range, about 16,000. Some are a little bit less. This makes a big difference when I'm up here. With the file size that comes out of this, not a big deal. And then I come up here. So again, you see the block size. I'm going to leave this out, base channel in black. I do that once in a while, depending on what I'm analyzing. And then all modes selected. That means all the screens will show up. Again, the same thing, the block size, and then the number of averages. I usually find for what I'm doing, 3 averages is more than enough. You can play with that, 5 and 10 averages. It'll get rid of some of the noise. That's basically what that's for. So E2000. Now this is the real guts of what we want to play with. So here's my recommended settings. So analysis graphs always auto scale after zoom. Good. That's good. Trust me. Generate peak file list with calculations. I can go either way. Usually I just leave everything checked. The ones that are showing right now are positive, are the defaults. Display motor efficiency, use background, include plots and report. Display phase-to-phase voltage data for 3-phase motors. and then also display unidentified peaks prompt. What that does is identify bearings that you have not included. So primarily unidentified peaks means you've got some multiplier times RPM that's not an integer that shows up within the alarm settings you set. And then allow positive calls to that. You leave that unchecked to allow the potential of false positives. Personally, I prefer false positives because then I can go in and analyze it myself. And then analyze and return short, especially with a VFD. I use that to make sure it's tuned or not. The line frequency coming in, if you're in Europe or Asia and you've got 50 hertz, select 50 hertz. In the US, we use 60. And then high frequency download length in seconds, 9 seconds is average. And then here, DC value only is what I use. Those are the defaults. Here, I can change all the different colors for the channels. You definitely want the extra tabs selected. That is going to show you torque and a couple other things. So I usually check everything here as well. And then last but not least, the alarm settings. So minimum load to call a rotor bar, I like to leave that at about all the way down because I detect all the time when I have that block setting selected. Now we're taking 12,000 samples a second and a 65,000 block size. That means I have so many lines. I've got very sharp peaks, and I have frequently gone in after a motor's been repaired, sitting on a test bench, disconnected regardless of size, and been able to determine if I've got rotor issues. That's primarily what that's for. It's because you need peaks to separate away from other peaks. And then the flag amplitude, I set down a little bit lower and detection down a little lower. So it will tend to flag me things earlier than intended. Belt slip, because I do a lot of belted applications, I usually just leave it about 2%, so it reminds me to take a look. And then down below here, you can stretch this all out in order to see more, but this basically gives me the harmonic limits if I want to select those. And that's it. So once I have all that done, the software is set. Now, I only have to do that once. I don't do that every time. So that is meant for one time when you first get the system. You want to make sure all your settings are correct. Now let's get into the fun part. So we have this 600 horsepower pump on this plastic table next to me. Let's go ahead and test it. So we're going to call it, we're going to use the column on the side. Just to put this into perspective, we are going to, we're going to set it up this way. So I'm going to call it something, let's say webinar. Okay, that's what I'm going to call it so I don't accidentally mix this up with the real data I have. And then I can either click the checkbox or hit enter, and I'll do that. So now I show up here. Now some of the things I'm looking at up here, angry face means exit. And you notice when I have things on, when I highlight things, it'll tell me what it's there for at that time. This one will show up in your instance of the software unless you're using the ECMS or EMPATH continuous monitoring system. So this is for doing trending. We'll take a look at that in a minute. And then this here is if I'm doing a continuous monitoring, that turns that on. That is something outside the scope of today. We'll do that in another one. So when I'm in here, now I can start doing a few things. This allows me to flip between two sets of data. I'll show you what that is when we get there. But I'm going to create a new folder. The folder is the motor in this case. I can do other things with that, whatever you want. It's a Windows folder. You can put it anywhere, including in the cloud, for Windows. I recommend you collect the data directly to your PC, and then you can sync it to the cloud later, because otherwise you're relying on your internet connection. That could be as good as the one I've got today. So let's say we're going to call this webinar again. So it's webinar motor, and it will do its thing. And thank you very much for not doing it right there. Rename. We're going to call it webinar motor. and it doesn't want to do it. Okay, so let's go back in here. We're just going to dump it in this part here. There we go. Let's call it webinar. You guys know that I didn't practice this first, right? So what you're seeing is real life, what happens. Good news is I can go back anytime and change that to whatever I want in the Windows folder. It does not damage, distract, or do anything to cause problems. So here we are. Now, when I have this set up, I just double click it. I'm in my data collection screen as long as I'm connected to the EMPATH. Okay, so not too bad. Only 15 minutes into it, and we're going to be done within the hour and then some. So come across the top. Everything here is also in here. Okay, so this is all the same thing in writing. So it'll tell you what it is. These here, happy face is going to be what we spend time on. Display layout shows me which channels I'm looking at. When I come in here, this is the amplification of the transducer. 10 millivolts per amps is default. But the nice thing is if you have a BNC current clamp of any type and you plug in, you just put the conversion rate in here on each of the channels. So for this, it'd be 1, 3, and 5. 2 is voltage, so that's going to be different. 2, 4, and 6 is voltage. Okay? So when I'm in here, 10 millivolts per amp, that means that whatever I've connected up will do that. And then this is basically part of my gains. Okay, so we're done with that. That's telling us that what we're seeing here is going to be 3 phases of voltage and current. Across here, single all and single phase or all. This speeds up and slows down the scan on the screen. These are zooms. This is the number of channels that it'll be showing. This is the sampling rate, which is set maxed out at 12,000. Okay, a lot are 6,000 or less, but we're going to stick with that because, you know, I like my everything else. I can change the resolution as well. I'm going to leave it where it is, the default. This gives me, I can watch a real-time spectrum. This is set a trigger level. Now that's what we're going to do first after we set up the nameplate. This sets the length of the download test, begin download, etc. So we're going to come in here and play with these after. So first thing we want to do when I set up webinar is put in my nameplate. So here we go, nameplate information. You can see I've got certain things here. So first thing is it's a VFD application, so we're going to select that. We do have 3 phases of voltage and current, so we're going to set that. We don't need to find these, and I'll show you why. So if I come over here, this is going to be a pump. I select the same thing for pump or fan. I believe there were 6 blades on this one. It is a totally enclosed fan-cooled motor. It is premium efficient. And then we start down here. So the machine was 600 horsepower, 1789, 460, 652 amps in full load. Okay, and then I can set a minimum current if I want. Usually that would be about 25%, 20 to 30% of full load is going to be the no load current. We're going to leave this where it is. So I come to rotor bars and stator slots and I go, what do I do there? Well, very simple. Down below, motor database. We know it's a Baldor, right? So let's go ahead and select Baldor. Now, because it's a 600 horsepower, 460 volt motor, I don't know if that's what I'm going to get. So I hit enter, by the way, and I get that. Now I can get this out of the way, and I can scroll down through these until I get around a horsepower I'm interested in. It's a Baldor, so there's a lot. Here we go. So when I start down here, I also want to look at the RPM, and I can start seeing different patterns. So 500 is here, and I've got 5011 size. That's pretty close. Now, why is it important to take a look at this and say, okay, what's going on here? By the way, yeah, so 54 and 72 looks to be pretty common, okay, for 1800 RPM in about the same frame size. So if I don't have it, I can start here. The other thing I can do is take a look at, say, the ESA database if I'm a service center. But I'm going to go ahead and suggest that it's probably going to be 54 and 72 because it's fairly common here for about this frame size and the speed. Why would I select that? And if I look up at the other ones, it's going to be very, very close. Why would I select that? Well, part of the reason, and up here at 450 and 460, so 46 and 60 or 54 and 72. The reason is because manufacturers don't like to have all different kinds of stampings. It's not cost effective. So often this will put me in the right direction. If I don't trust the value, I can have it auto select and it'll look for certain patterns instead of that. This, if you put in the number, it's very exact. So I'm going to suggest it's probably 54 and 72. I think I actually counted them and they aren't. But so for here, we'll call 54 and 72. Now CT ratio should be 3 for the actual application, but because this is a little half horsepower motor and it draws about an amp, we are going to put in 600 and see what happens. Right voltage, or no, that's not the right voltage. So we're going to put in PT ratio of 2. Okay, so that just multiplies what's coming in by that, so I can increase the value. There has been occasions where I've needed to play with that number. So now we also know we have a 6322, and then we can now do 2 additional ones at the same speed as the motor. So let's go ahead and we're going to open this up. We're going to select an SKF because, you know, why not? That's the thing we used. Wait until it says to stop, please waiting. Okay, and there we go. And I put in 6222, sorry, 6222. Click OK, and that puts all my multipliers in. Do the same thing for this one because they're identical bearings. Why not? I could technically put in a different thing instead of opposite end there and actually increase it to 3 bearings. I do that on certain gearbox applications. There are little tricks you can do. Okay, 6222 bearing. And we're just going to call them 6308s for the pump. So pump DE, so that would be motor side. And just for time, I'm going to go ahead and just do 1. Because I actually don't know if this is the right size. So 6308. But just to show you, there's 54,000 bearings roughly. And what was really surprising, the main bearings of wind turbines are even in here. And those bearings are massive. So there's quite a bit in there. So now I have my nameplate in and I'm all set. So let's go back, double click on webinar. We're here like we talked about. Now, what I want to do is set a trigger level. Now that I have all the other stuff in, I can come up here, say set trigger level. And then what I can do is come down here and select and draw it up a little bit. And so now I have a gray line and an approximate value. Okay, so the next thing I want to do is click my download. And this will allow me to set a length of time that I'm going to collect data. So when does this come in handy? Okay, I had a DC machine, a very large DC machine, and we knew that it had 11 passes on this particular application. It was a roughing mill. So we figured out it was about 240 seconds. So I set it for 300 seconds, 5 minutes, and just let it run. So it would start and then it just ran for that length of time, got all the data. Okay, so the first one we're going to do is this. I'm going to leave it for 48 seconds, and we're going to go ahead and click OK. So now you see it's waiting for a trigger. And there it goes. So as soon as it selected that, and it's going to continue collecting across that length of time. And I apparently set the CT ratio a little high. 1200 amps, woohoo! But remember, that's RMS. So what is it saying? Amps is actually coming out to be, yeah, something less than that. But in any case, yeah, so it's showing a little higher than I expected. But you know what's kind of cool? I can change that afterwards if I need to by changing that CT ratio. The good news is what's happening is all this data is coming and it's raw. It's kept in text, it's kept in the files, and that means that's something I can work with afterwards. So I'm going to go ahead and turn that off for now. So this is roughly what it grabbed. This is now set up. And depending on the application, it can pop up my calculations tab. And I'm going to go through some of this stuff in a second. What it's doing right now is kind of thinking through the application. And my computer's obviously thinking through a few things too. So anyways, as we come across here, here we go. Results, okay. Looks all right, just off the straight skinny from this. Across here, close, of course. Happy face is my header information, and we'll take a look at all that stuff in a minute. This is a display, so I can select channels I want to look at. And then these two down here are power. That means kilowatts. So I can add in kilowatts. Okay, so that's a kilowatt FFT. I can also change these. So instead of looking at that, I can change these over. Sorry, my bad. Change these over and then go like this. Just click and drag them down so it shows all the channels. And then this will show my FFT for those as well. Now, it'll do a high, when I do this type of data collection, it'll show my high frequency one. Now down here, I've got the same type of thing. This is actually one time. These are sidebands up here. I can do some funky stuff with this, including changing that. So up here, I've got different tools. Most of them are on the buttons. Layout allows me to do some additional stuff. I usually use flat top for analyzing. Here, this is what Hanning does. Okay. But let's go ahead. I use flat top myself. You can use Hanning, very similar to what you use in vibration. And then zooms, go in and do different zooms, and then all kinds of other stuff here. We'll get into that in a minute. And then I can change the minimum dB level. Some applications, you'll see that this noise floor drops below. So what I end up doing is I will change it so I see the noise floor as well, because there may be things I'm looking for. I can switch it from Hertz, what it is right now, to RPM, depending on what your background is. Then different types of log spectrums. I usually use relative for my analysis. And then I can also change this to linear. What this does for me when I'm analyzing down here is it gives me absolute values. So if I come in here and I'm looking at it, also, like I said, it also changes that up here to current. But if I see a specific issue, I can come in. So blade, if this was a blade frequency here, its value is about 16 kilowatts worth of energy. That would be a defect if that was actually it. So in any case, that's one of the things I can do there. And we're going to get out of this so we can go back and we're going to run a regular run a regular data collection. But let me cover some of this first, and then when we do the analysis on regular data collection, we'll go through pretty quick. This is my X zoom, so I can go into an area and zoom in. Okay. This lets me step back if I have multiple zooms. This is my vertical. This is auto scales it to the trace. I can look at the zoom region here. It sets up different things for me. I can look at statistics. I can have both up at the same time. I can put in labels. Can do that anyways. I can print these. This will allow me to say, come in here and do a waterfall that I can also zoom in on. And this allows me to look at specific issues as we go through analysis. Okay, and then this one here, the calculations, it's thinking again. We're going to get into this a little bit more when we're analyzing the real information. There we go. Okay, so here we go. We got all this stuff here. Bearings look okay for the bearings I selected. And you'll notice it has all of them. And then this gives me my harmonics, etc. And here is the cool one. This gives me a instantaneous torque graph, air gap torque. This gives me a torque spectrum. In foot-pounds here, I didn't point that out, but I can switch over to metric if I want to do everything in metric. That'll change it to Newton meters. And for the way I just did it, this is what's trended. So if I put this into the database, it will trend based on that. So all I'd have to do is hit populate database. This prints a report. This allows me to come in and set my running speeds and so on. And we're going to run slow today, aren't we? I'll wait until this is done. We're going to collect real data. Then we'll get into what this looks like on real info. Okay, so let's go ahead and get out of here. There's my data showing up from the Inrush. By the way, I could do an Inrush curve. That I didn't cover, did I? No. Okay, so let's go ahead, and what we're going to do is look at current envelope, and that's what the curve just happened to look like because it's on a VFD. If I started in Inrush, it would peak and then come right back down to where it's supposed to. So let's go ahead. I'm going to start this puppy up. This time, instead of doing that, we walk in. We got a machine that's running. Okay. We're just going to leave everything the way it is. So we already have it all set up. I can stop this to take a closer look at it. I can also set the gains automatically. Now this may mess with some things, but let's see what happens. Okay, so if I go in and I don't agree with something, then it's going to give me a rough idea of where everything is. I'm going to say okay, and then there's my information. I can change the length of the download. Okay, right now it's set for a default of 46 seconds. I can view what we're looking at as an FFT. As a matter of fact, let's go ahead and change this over to the log spectrum relative. And so this is going to give me everything I'm looking at real time. My scan rate's way off right now because I have so many inputs for this. Okay, so let's go back to where we were. Let's change this guy here back. Linear. Let's turn you off. So we're looking back where we were. We set the gains already. This just stops downloading. And by the way, if you're in the middle of a download and you've got whatever amount of time and the thing is stopped already, you can hit stop. It'll ask you if you want to save it. So we're going to go ahead and download. And when it immediately starts to just grab the data. And again, about 46 seconds. So we're on track. That's good. When I'm out collecting data, I usually try to get all this up front. Here's another nice thing. If I don't have the data for the machine, like the nameplate data, and I go out, I can set my folders up already or not. I can do them on the fly. I can download the data regardless, and I can update, but you have to update each set of data then for the machine. So if I go in and say, I didn't know the nameplate, that never happens when you're in the service industry, or the nameplate's missing. I can go in and go ahead and there we go. Yep, definitely exceeds the nameplate. So as soon as it finishes, it pops this stuff up. But anyways, I can go in, collect the data. I just have to create a name, do all the same steps, leave the default 1 horsepower motor in there, collect the data, go back later, change everything. I'm good. So normally what I'll do is if I get a call and the people have no idea what they're testing at, we've got 6 motors. They're all 460 volt. I show up and they're not. They're all 4160 volt and there's 7. I can then just do it on the fly. So collect the data, take pictures of the nameplates, go back, sit down, enter the nameplates into that data, and I'm good. So just real quick, here's what it thinks it saw in RMS. Yeah, a little high. Frequency, bearings, harmonics, voltage, and current. It'll also give me the actual values. And in the report, and I can change this to a different number of harmonics and so on. So I don't have to just accept that. I can change this and say, I want to go out to the 51st harmonic. But didn't like that, sorry. I can go out to, let's just leave it the way it is for right now. But I can go out to, say, 31st. Good. Not going to argue with me right now. For whatever reason, doesn't want to let me do it at the moment. And then I can go back and you can see here. So I can go out to the 61st harmonic. And then here's the things that it basically will trend for me if I dump it into the database through here. Okay. And any cursors that it selected. This is the torque in hertz. This is in time. Obviously got something going on here. Probably after TSA dropped, bumped, and kicked this darn thing a few times, but that's neither here nor there. And then same thing down here, but we're going to skip that part. Real quick, come in. This is just the way it shows up for the default. I can come out here. You see all that mess that has to do with this particular VFD. I can go up into my high frequency. This is normally what I'll show for my analysis. Okay, I'll get this. Let's get that, whatever shows up here. So this is important. This gives you a certain benefit. Okay, so this will show here. Now, if I just want to analyze just this little bit, I just click X and watch the right screen. Okay, it changed a bit. Okay, I can also do that in the first one. That's often what I do in, say, elevators, where I only get like 20 seconds out of my 48. I'll just take that 28 seconds part I'm interested in. And then I can analyze this. These are the camel humps. That has to do with the drive and harmonics. And we'll get into that when we analyze the real data. So let's go ahead and take a look at some real data. So let's grab this guy here. This is the real 600 horsepower, as are these two. And we're going to open up this set of data here. I'm going to unplug that machine. There we go. So that things happen a little faster. So when I open this up, here's what real life looks like on a VFD that's changing speeds. Highlight the one I'm interested in. Let's zoom out. Okay, notice a little pile here. That means it wasn't exactly steady at 41.7 hertz. So I've got a little bit of stuff going on. I can take a look and see if that's consistent by clicking on here and selecting my waterfall plot. And then, if I wish, go in and take a closer look by zooming in. It's pretty wide, so that means it's constantly changing. Okay. I can do this for anything, and I'll often do it if I have a wide base. Say if I'm interested in this area here at about 85 hertz, and I go ahead in, and I come out to about 85 hertz. So that'll be this area here, and I click on X. That'll get me out, and I can see small variations. So if I have a lot of variation, I'll see it. This is all noise, so I tend to not pay too much attention to that. Okay, so let's see what we really have in the nameplate here. And I had messed up. So these are actually 6222s, right? So 6222. Click OK. 6222. And notice when I click OK, these are going to update. This is from that massive database. And I said we're going to call these 6308s because I just want to distinguish them from those. So let's call these 6308s. As you can see, this is all pretty quick. Very nice. Okay, so this is my calculation part. This stuff here, by the way, that you only get with the ECMS to get rid of a lot of false positives, but this is all for the report. The report's in Word, so I'll usually just type directly in. That's my thing. It is a totally enclosed fan cooled. It is premium efficient. Noting whether it is or is not will impact a few things. So I had determined 46 and 60 on this. So it was those values. And so now here I am. So I have this. I can go in and do different things, but what I want to do first is just let it auto-calculate for me. Okay. So it says loose connection. By the way, yes, there was. There was most definitely a loose connection there. Almost pulled it out while I was connecting the current clamps. Luckily, it was not running when we set that up. That's part of the reason, because I've done that before. Running, have everything, the suit on, you go in and you don't check the cable right away and you go to put current clamps on, next thing you know, you're holding a cable. Never do that, and it's another reason if you're doing any live work to make sure there's a second nearby. Long time ago, lesson learned, I was 20-something. So anyways, rotor bar health is questionable, C5. So that means that I want to take a look at that. That does not automatically mean I have a bad rotor bar. I don't see anything for bearings. I don't see interturn short issues and so on. So right now it's not seeing anything in particular. I will then, when I start analyzing, at about 10 dB above the noise floor or 65 dB down is when I'll also see it with other technologies. So those are usually the alarm rates that I use. So here's my nameplate. It's saying we're at 38% load. It's got a pretty good efficiency. Losses due to impedance unbalance. That's the loose connection. So I've got significant losses across that unbalance. I can look at this as horsepower instead. But across here, I'm expecting the power factor to be relatively low because it's on the output of a VFD. That's actually pretty darn good. Frequencies, the line frequency, running speed itself. If it can calculate a pole pass frequency, it will. I have not done the pole pass frequency yet, so it has not. This is the total harmonic distortion. That's a completely other lesson, by the way, as far as current. And then volts per hertz ratio. This tells me that it's not auto-detecting anything in the first harmonic of those. Fourth harmonic is when I start seeing the early stage bearing failures. And here's a couple other things here, and all my current and voltage harmonic tell me where it is. And then my extras here. This is the current captured in it, and there's my foot-pounds. Okay, and then what all that value is, I can, whenever I see this, I can print the graphic out. It'll screen capture it. Now, for my analysis part, let's go up here. Let's go ahead and I will right-click. If I just click on it, it does running speed only. But let's go ahead, running speed and pole pass frequency. So it's going to select a pole pass frequency. And because I set it up a certain way, you notice that this running speed is staying right in the line. So it selected 0.275 hertz as the pole pass frequency. That has to do with the slip times the number of poles. I did not lose my connection because that has to do with the calculated impedance per phase. And I'm all set. So just so happened on this one, we selected the right cable because we had 3 cables in a row. When I'm actually looking for loose connections where I have multiple cables, I'll use a Rogowski coil around them. So I have this now. I'm going to show I'm going to show you the report first, then we're going to go in and look at data. So let's go ahead and just have it generate a report. It takes a few minutes, but it will show me the summary of everything we just looked at there. It also have some screen captures in the back. This is one thing, Vedat, we really need to work on. Takes a little bit for it to open up Word. Actually, it's more a function of the laptop and the version of Word I'm using. It takes forever to open a normal day. So we'll give this a few seconds. I don't see any questions just yet. Let me see, and most everybody is still there. And if you are a user already of EMPATH, this will show up on the motordoc.com website the way it is. So I'm showing you the setup, the actual operation, some of the special features, and an overview of analysis, the automated analysis. And boy, it really doesn't want to open, does it? At this point, I normally get up, take a cup of coffee, and just let Word open when it wants to open. One of the nice things, too, about the software is it does not draw anything off the operating system. It's standalone, which is nice. Here we go. So let's go ahead and open this puppy up. So here it is. It is in Word. So there's a couple of things I can do. Okay. I can come out here just so it stands out a little bit. Okay. And call this whatever I want. I can come down here, and if I don't agree with some of the results, I can also change those. That includes all the way through. I usually tend not to play with it too much past that first page, because I'll personally come in here afterwards just to help people out. I can put notes, but they show up on a different page, and say, and then that'll stay. Okay. So come in here, nameplate information, descriptions, what it saw here, the current, the time. Okay, so what the RMS is, what the peak was, power factor, the impedance. So there's that impedance unbalance. So it had about deviation about 16.8. This is all the other stuff we had there. This is the information on the rotor bar health that it saw, the bearings, and as we continue through, I get into the graphics. Okay, so we had enough data to take so there's all of the stuff so that you've got that as part of your report. Okay, now if I spent some time on torque, that would also show up. So that is the report. Not going to save that. That is this part here. Up here, let's see, I can drag down if I'm interested in a particular area. You have to estimate what the peak is because I can't highlight anything yet. To go back, just go from right to left instead. And that'll allow you to go in and make confirmation on some stuff. So this is my low frequency data set. What I want to do here let's take a look. Now I've got a peak in blade frequency. My blade frequency is 41 hertz. This is 40, so somewhere around 80 I should have a peak. So most likely between 42 and 42, that should be 84. So that would be this peak here. So I've got one half of it. The other one is probably just on the outside here. So that's a peak having to do with the blade frequency. It's above 65 dB down. It's definitely 10 dB above the noise floor. So I know I have a problem with the blade. Boom. Okay. For this VFD, is there any standard limit for current harmonic? Okay, actually current harmonic is current dynamic distortion, which is a whole other calculation in IEEE 519. I'm going to do that as a separate seminar on harmonics. But on the output between the drive and the motor, no, there's no real limit. It depends on what type of filter you use. I'm going to talk about that in a minute. Most medium voltage or high voltage drives don't have CT-PT secondary. Can we do this test? I usually at that point will use just the current clamps. Okay, so I can still do this. I'll lose torque and I lose kilowatts, but I can still do, hell, I can do current signature analysis off of one phase if I needed to. And then for VFD, the current is always high. Yes, it is, because this is an RMS meter. And what happens is for this type of data collection, if I used a true RMS data, which would give me an actual value, what ends up happening is it filters out everything. So where I go is I use an RMS type meter, a power analyzer basically. That's what these are. And then I take that data. So everything you'll see is basically refers to RMS. So things like true power factor and things like that, I won't necessarily see in this part of the analysis. So true RMS takes the current and voltage harmonics into account. Okay, so that should answer the questions I've got so far. But yes, I'll talk if we have time today, but we probably don't. But I'll be covering what total dynamic distortion is and how to do that. I think I covered it briefly in a previous one on power quality. Okay, so I'm in here. I want to look at my high frequency data set. My computer's still thinking today, and gives me a rough idea what I'm looking at. And you can see all this nastiness here. By the way, there's a filter issue on these. That's, you know, neither here nor there. This was part of a commissioning of a set of drives. So we zoom out. I want to make sure I do that first. Okay. And this is real data off of 600 horsepower direct, other than the CT ratio of 3. I can come in here, and if I want to add in that kilowatt, I can. I don't do at this point, but I usually use that in order to determine my severity of the fault, because when I go into linear there and I find a fault, that will give me the actual losses across that fault. And anything that's 10% of the total kilowatts is urgent. It'll vary from there depending on the application, but that's generally what I use. So let's go ahead. We're just going to take one channel. So I just get rid of these guys. And that brings me down to a single channel. Blue is pretty. Up here, I can do the same waterfall. I can do all the other things I showed. And I can also do this. I can come in. I always want to show power harmonics. And then let's see if I've got static eccentricity. That means that the rotor sitting off to one side. Okay, very possibly it lines up very, very close to line frequency. And if I want to verify it, I'm getting close, because one of these is line frequency and one set is not. So I come down here. The other thing I want to do is say this is showing me 74 dB down and this is showing me 69 dB down. This is taller. The lower number means taller. So this is just a power harmonic. Boom, done. If my voltage is higher, it's from outside the machine. If it upstream, so it'd be VFD related. If it's higher in current, it's the machine. But let's see about whether or not the rotor's orbiting magnetically. And it could be, I have to go in and verify my speed. Okay, but it's possible. Then let's take a look at mechanical, stator mechanical. Yep. Okay, so something going on with the windings. That will immediately have me take a look at something else. So let's back out of there and come over here and take a look at two things. One is, oh, and by the way, there are blade peaks right here. 166, 64 dB down, 72 dB down. That's a blade. Pretty straightforward. But I can come in here and let's take a look at interturn short. Now, what we discovered, and the paper is being presented this week through IEEE, is if I see interturn shorts here, even though the motor hasn't failed. Now, if it's on a drive and I have an actual short, it trips off. But what happens is I can have discharges going on between conductors and things like that, and that will interrupt the magnetic circuit, and it looks like arcing or a short. So what I want to do is verify that I have peaks outside, like this peak here and a couple other peaks. And if they don't associate with anything else, then that just means that the drive isn't tuned properly, or, and I know that was the case, or they selected the wrong filter. That's kind of what I'm looking at there. Bearings, let's see. So if I want to get in closer, I can. Here we go. So bearing, there's possible bearing. Possible bearing, that would be the inner race. That would be, oh, that's the ball. This would be the outer race. If it was on a peak, it's not. So that will show up. I had one of these just recently. I actually have the bearing from a wind turbine sitting over on my other desk here. They said, oh no, it's not the bearing, and yeah, sure was. Matter of fact, it looks pretty ugly. So anyways, yes, and if I'm seeing it at this value, the one time, then it is a bearing issue. It is detectable with vibration. If I see the second, third, and fourth harmonics, that is varying degrees of urgency. When I sit down, I'll usually calculate those out in a spreadsheet and look for those peaks if I want to detect something early enough. So anyways, that is that part there. What else do we want to take a look at here? Okay, loose on phase one, we already went through that. Okay, so that is most of the stuff. So the stator, it says stator mechanical damage. What that is basically the running speed times the stator slots plus and minus the line frequency. When I see that in a VFD application, it can also be related to little discharges going on between turns. It's a random well machine, not too surprising. And when I have those type, and here's, by the way, where I step back. There's a single hump here versus others, and you'll see all those will line up with these peaks down here, which I call the Christmas tree. Let's see, any last or least things I want to cover on here? I think I covered almost everything. There was couple of more things. There's a lot of other features in here. Oh yeah. Right now you see it says low. I can switch those over to say high and then go straight to the high frequency set, especially if I'm doing a comparison. And that's what I meant to do. So you see I have 3 sets of data here. Here's something I can do, and I can do this with as many sets of data as I want. Let's go ahead and get this done. Okay, so I have this set of data. How did it compare to another set of data? So I want to add. Doesn't want me to add. Why don't you want me to add? What did I do today? Okay, let's try it from here. Oh, it had me add the same one. Okay, so let me go ahead and select that one and that one. Let's go ahead and open them both. Okay, so that's the other set of data. No, it didn't open it. All right. Not sure exactly why it's preventing it, but there's normally a reason. So anyways, I can add two sets of data on top of each other normally. Yeah, it's not showing up. Okay, I must have a setting set a certain way. That'll happen on occasion. Not going to try to fix it on the fly, but I can set these right on top of each other and do a direct front and back. I can flip between them and see what's changed. I can change the channel colors in order to look at a comparison. All right, let's try this. So I had things open, it looks like. If you're wondering what that thing is in the background, that is the John Deere hybrid tractor I helped design, and it's got 485 kilowatt motors in each of the wheels and two good-sized generators. Let's see if we've got it now. Yep, there it is. Okay. So I had something open still that I forgot about. Let's add a file. There we go. You notice there's some changes up here. Let's get these all zoomed in so that when I compare, they're the same. Okay, now you can see I can switch in between. So this is the previous one, this is the new one. I can lay them on top of each other. Okay, and you see that it's slightly off, but I can still take a look and see what's going on. I can do my analysis over everything. Now, if I go into high frequency here, I can't necessarily go into high frequency at the other one. That's why we have that ability here to switch, so that if I'm looking at my high frequency data set here, and this will finish it, by the way, and I want to add this one. Okay, let's flip it back over. Okay, there we go, and let's compare them. So there we are again. So I can do that now. Hey, let's see, what did the other one look like? At this point, you want to pay attention to the dates. Okay, so you see this in even lighter color. If I sit these on top, I'm now looking at all three. I can also cycle through them. As you can see, I now have three. Okay, so when I do this, I'm looking at all of them at the same time. I can look at a whole history if I want. So that was a relatively new feature once we hit version, whatever version we're on now. In any case, that covers, when we hit about 7. That covers most of that, and that's a good solid tour of the EMPATH. Please feel free to reach out. You're going to receive a certificate, yes, 1 hour towards CMRP still, and I'll also follow up with the link to the other goodies from the past seminars if you want to go in and watch the ones that are there. There's a secret folder with data analysis stuff created by or assembled by one of the distributors and so on. So if you have any questions, feel free to reach out afterwards. I don't see any additional questions here. We've only run a few minutes over, so have a great day, stay safe, stay healthy, and we'll talk more later.